Thank you so much for the kind introduction. Can people hear me okay? So again, let me repeat what everybody else from Indiana University has said. Welcome. It is a thrill to have the Galaxy Community Conference here at Indiana University. I've got to start off by saying that, I'm here using a slot of your valuable day because the Pervasive Technology Institute is a sponsor, and it's at least a little bit lame to give a pseudo-technical talk in a sponsor's slot. So I feel a special obligation to try to make sure that I make good use of your time. And so my goal today is to talk about the evolution of cyber infrastructure, the evolution of biological research, and particularly talk a fair bit about a new cloud-based system that Indiana University, the Texas Advanced Computing Center, University of Chicago, Johns Hopkins, and others are deploying called Jetstream. And I want in particular to give you enough information about Jetstream that you consider it as a potential resource for your own research. And I will tell you that you may actually already be using it already without really knowing about it. So I'm going to talk particularly in ways about U.S. researchers can use Jetstream, but Jetstream is actually accessible to anybody that's using Galaxy. It's just a little bit harder if you aren't a U.S.-based researcher. So we'll talk about Jetstream. I'm going to talk about Galaxy and Jetstream. A little bit of biology to show that you can actually do real biology with Jetstream. Real biologists have done it. And then I want to talk a little bit about how cyber infrastructure and research computing generally is evolving with biological research. And then at the end, I will talk a little bit about how you can get your own personal allocations to use Jetstream for Galaxy or your own tools or whatever you want to do. So a little bit about Jetstream. Jetstream is a cloud system. It is funded by the National Science Foundation. It is the first cloud system that was ever funded as a production resource for the scientific community by the National Science Foundation. So it's a new thing. We have intentionally modeled it after commercial clouds. We've got a small test and development server that sits with our partners at the University of Arizona in Tucson, where we do sort of our test deployments. We have two production components to the system, one sitting in Austin, Texas, one sitting in Bloomington, Indiana. Those of you who went to the CIB last night and took the data center tour probably saw the Bloomington half of the production part of Jetstream. In terms of the hardware, there's nothing especially special about the hardware. Half a petaflops of capacity, Haswell chips. The Haswells are really nice. We really like the performance. But by supercomputer standards, it's not huge. In terms of supporting research, it is intended to be up 24 hours a day, 365 days a year. We are intentionally trying to make it available for researchers whenever they want to use it, wherever they want to use it. And we are designing it specifically to be easy to use. By the way, I should say just very briefly, I will post these slides with a CC by 3.0 license on them, so if you want to see some of the slides, you'll be able to get right to the PowerPoint bits just within a couple days here, if you wish. And I should also say that I'm going to be using some slides from James Taylor. So Jetstream is designed for biologists, for observational astronomers, for snow and ice data researchers. It's designed for end scientists to improve scientific research. It is not designed for supercomputer people to feel good about how cool and how big and how much electricity a supercomputer uses. So the real core need that we're trying to meet with Jetstream is, a researcher wants to get to the tools that they want to use to analyze their data. They want to do it now. They don't need 5,000 processor cores. They don't want to wait a week. They want a handful or a few handfuls of processor cores. They want to do it now, whatever fits in the natural research activities of a researcher who's going about their everyday business. There's another need that we are hoping to meet, which is software tool developer wants to get her or his tools out where other researchers can find those tools and make use of them. We want to facilitate reproducible data analyses. I really enjoyed the first talk this morning, and the insight that it's okay to be wrong as long as you're reproducibly wrong so you can figure out what happened afterwards. That's a really important point. So we're very interested in supporting reproducible data analyses, and we also want to support science gateways and other interactive tools. Galaxy, I noticed Paul Stewart, with whom I'm not related other than our shared great heritage from Scotland, I believe. Paul mentioned setting up his own server in a way that sounded like it was a little bit of work at least. So we're interested in setting up gateways and servers for people on Jetstream. For those of you who have used iPlant, the Jetstream interface is the Atmosphere interface developed by iPlant. Really very simple, very intuitive, well known to a significant set of the biological research community. You authenticate to Jetstream. You are presented with a list of virtual machines that are published and publicly available. You pick the virtual machines that you want to use, you fire them up and you go use them. If you want to use R, if you want to use RStudio, if you want to use Mr. Bayes, you can get to any number of virtual machines configured to do a specific task and run them yourself. And you can add data in them, you can customize them, you can build your own virtual machines, and then you can save them in your own private library. So it's a very intuitive thing to use. And then, of course, the other way to use it is simply to use a Galaxy gateway interface and run jobs on Jetstream that way. So it's designed for biologists by at least ex-biologists. And what's special about Jetstream, as opposed to some other cloud, Amazon, Microsoft, Azure? Why was it that the NSF decided to invest in this idea as opposed to giving people checks to send to Amazon? First of all, Jetstream is designed to support research workflows in ways that meet researcher needs. So we don't have extra charges for storage, we don't have extra charges for data movement, we don't have charges for CPU time. The use of Jetstream is paid for by the NSF, and it's essentially metered by the capacity of the system. So crunch all you want. When we start hitting capacity levels on Jetstream, we'll go to the NSF quite happily and say usage is up, we need more money to make the system bigger. We are leveraging the Atmosphere interface as much as we can to have it be a known quantity for the biological research community. You get to live in your own little world inside your VMs. I live in my own little world. Everybody there knows me. I like it a lot. You can have your own little world inside Jetstream. The National Science Foundation never gives anyone enough money to actually stand up these systems, make them work, and support them. So part of our very explicit strategy with Jetstream was to depend on existing community structures, existing virtual organizations, existing communities of practice, and leverage structures that already exist in science communities, like the Galaxy community, the Galaxy Community Conference, so that we can put a resource out there, and then if you all decide that it really is actually valuable to you, the existing support and training structures, which we have already seen in such good evidence here in the last few days at the community conference and the tutorials, those become ways by which we can disseminate information about Jetstream and let the community help itself make use of Jetstream without having to have the NSF pay us to do tutorials and that sort of thing. So we are explicitly trying to leverage structures like the Galaxy community. And the cosmologists and the physicists and the protein folders, they've gotten plenty of money from the NSF in the form of systems that are designed to support that type of research. So with Jetstream, we're really focused on the complement of people who have used NSF-funded cyber infrastructure for a long time. Us, real biologists, observational astronomers, some of the earth science community, engineers, and that sort of thing. I want to talk a little bit about reproducibility and things that we're doing within the Jetstream project to promote reproducibility. We actually are offering to users of Jetstream the ability to take a virtual machine, bundle it up, put it in IU's persistent repository, which is called ScholarWorks, and attach a DOI to it. So if you are publishing a paper, if you've got a paper in review, if you've got results that you want to make available in ways that allow other people to reproduce the analysis you've done and extend it, you can bundle everything you've done, from your input data to your scripts, to your programs, to your output files, and put that all in a digital bundle that sits in our persistent digital repository. And, you know, forever is a long time, so promising to store something forever is a bad idea. But the IU Digital Repository is 17 years old now, and for grant purposes, what we promise is at least 5 years beyond the end of any funding support. So in terms of Jetstream, we're talking 9 years minimum, and, you know, the president's commitment to this storage system is as far as we can see into the future. So we have a way for you to distribute your analyses in a way that allows other people to download them and put them in Jetstream or any other OpenStack cloud and just run them right away. So a little bit about Galaxy and Jetstream. A couple slides from James Taylor. I suspect that almost everyone here, maybe everyone, has seen these slides before. You know, the whole point of Galaxy is to promote ease of use and reproducibility of biological research, bioinformatics research. You know, again, another slide from James. Accessibility, transparency, reproducibility. So, you know, to sum up, what do we want? We want to be able to do our research. We want to be able to do it when we want it, when we need it. And we want to disseminate our analyses in ways that support the biological research community and give credibility to the research that we're doing. And you may actually have already been using Jetstream. So Jetstream is just about to transition from this odd phase that the National Science Foundation calls early operations into full production status. So while it was in early operations phase, our job was to convince the National Science Foundation that we had actually built the system we promised that we would build, and that it actually worked. And one of the best ways we could think of to demonstrate that it actually worked was to have people using it, doing research. And so the Galaxy portal on the galaxy.org website has, for months now, been draining jobs off to Jetstream, and this is a chart that is up to date as of the end of April. So 758 distinct users have made use of Jetstream, probably without knowing it. And this is a plot of frequency plot of number of jobs. So somebody out there has run something in the thousands of jobs. A whole bunch of people have run a couple jobs, but it's working quite well. And according to Anton and James, there is a fair bit of work that's going from the Galaxy portal on galaxy.org off into Jetstream. There are several ways to run Galaxy on Jetstream. Like I said, just from galaxy.org. We actually have a Galaxy instance up and running and accessible from Jetstream directly. Now, I should say that in terms of ways to run Galaxy on Jetstream, one of the differences between various ways is with credentials and with allocations that the NSF knows about regarding you as an individual user, and without. So if you run off of galaxy.org and your jobs go to Jetstream, sort of out the back end of the pipeline, you're actually running on an allocation that the National Science Foundation has given James for the entire Galaxy user community. You can get a personal allocation or a group allocation directly on Jetstream. and we've got a Galaxy portal running on Jetstream. We also have it running in an individually instantiable way through CloudMan. So 3 different ways to use Jetstream, and just a little bit of biology here just to show that you really can do stuff, because it's easy to talk about how great a system is. Showing that somebody actually did some research with it is kind of cool. So Marlis and Michael Douglas are 2 biologists at the University of Arkansas. This is where they do their field work. Out in the Colorado River Basin. This is sort of a map of them in field season. Endangered fish here, Marlis Douglas right there, and rattlesnakes essentially everywhere you go. And they have done a couple of research projects where they did analysis on Jetstream. One was with the genetics of fishes endemic to the Colorado River, and these are fishes that are very often endemic to a particular part of the Colorado River. They are endangered by any number of things, dams. That right there is a striper. Now, catching a striper that size out of the right place to go fishing for stripers would be a great thing to do. Catching a striper out of the Colorado River of that size means that native fish have been pushed out of their native habitat. So the Douglas Lab had sitting around a bunch of DD-RAD data that they had not been able to analyze for lack of computing resources. So as I was hunting around for people to use as examples and talking to the NSF about, hey, the system actually works, they were sitting on top of data that they couldn't analyze because they didn't have compute resources. So they did some very, very interesting work, and I don't want to get ahead of them publishing their work, but the summary of their work was that the DD-RAD analysis of some of these endemic fishes shows a lot more reticulate evolution, a lot more history of crossbreeding between species than one would typically expect in this sort of highly geographically isolated area. They did very similar works with the Western rattlesnake complex. This is a complex that they have studied themselves on a morphological basis in the past. And this is kind of cool from an ecological standpoint in terms of species preservation. Also, if you happen to be bit by a rattlesnake, your recovery will be greatly aided by getting an antivenom that goes with the right species that bit you. So knowing what species you're actually dealing with is very, very important. And the summary of their early work using Jetstream, again, to look largely at DD-RAD data, is that they think they lumped too much on the basis of their morphological work, that there's really several more subspecies in the complex than they thought there were originally. So a little bit about cyber infrastructure and the coevolution of cyber infrastructure and research. This is a Cray YMP, the sort of supercomputer that you would have used if you were able to use one of the big supercomputers at the National Science Foundation funded supercomputing centers in the 80s. They had this sort of time machine function. The idea was to take a very small number of people and transport them into the future of computing capabilities so that they could solve well-known, well-formulated, and important questions like, how did the universe begin? How does the atmosphere work? What makes tornadoes? Really wonderful machines, very, very specialized, very hard to use. Somewhere along the line, the NSF decided that they needed to expand the applicability and the scope of the sort of computing resources that they were funding. And, we all know that it's a bad thing when a federal funding agency invents or popularizes new words. It's just never comes to a good end. And cyber infrastructure is one such example. There was this report that came out in 2003 that talked about how important cyber infrastructure was without ever defining it. This report said, cyber infrastructure is really important. The NSF should invest in it. Don't know what it is. And so you'd have people from the National Science Foundation saying things like, well, cyber infrastructure is more than just supercomputers. And cyber infrastructure includes, but is not limited to, advanced data resources. Being a devotee of the standard English subject-verb-object sentence form, several of my colleagues and I came up with this definition here. Cyber infrastructure consists of computing systems, data storage systems, instruments, networks, software, and people all linked together to do things that would otherwise be impossible. And the NSF has this nice diagram that shows how cyber infrastructure and data and people fit into sort of a nice depiction of how research is done today with, highly automated instruments, lots of data, and requirements for lots of computing. And what we've seen over time from the 80s to today is really a change in the way computing systems and research interact with each other and evolve. So I said in the 80s, the NSF-funded supercomputing centers really sort of served this time machine function. And then somewhere along the line, the 90s or so, they became MPI machines, message passing interface machines. And I remember listening to computer scientists and astronomers tell biologists that if you wanted to use these great machines, all you needed to do was spend a year as a postdoc learning how to write MPI programs properly. And once you did that, you could use these glorious supercomputers that the NSF was paying for. They got a few takers on that, but not very many. With Jetstream, and I think ever more as we move forward, and this is true of some of the other NSF-funded systems as well, what we've really seen is that the science needs are driving the design of the system. And with Jetstream, we've seen this definition of cyber infrastructure play out in ways that I never anticipated to begin with. When we first wrote the words enable breakthroughs not otherwise possible, I was thinking really big supercomputers, really big simulations that couldn't otherwise be done. And with Jetstream, what we've seen with the Douglas Lab as an example is not otherwise possible means presenting computer resources to practicing scientists in ways that are accessible to them on the time scales that the scientists need to do research that isn't otherwise possible because they don't have the resources that match their needs otherwise. So I think we see with Jetstream a real inflection point in the design of systems where the systems and the hardware are being oriented around the research needs that are being solved. And in this regard, Jetstream, I think, very much follows some really important software examples. Galaxy, iPlant Cypress, Mark Miller's in the audience here. Great examples of software built around solving a particular problem. And I think we've seen that expanded now to Jetstream. And I put Moore's Law in the title, so I wanted to come back to Moore's Law very, very briefly. Without going into gory detail, what Moore's Law says is that CPUs and computers get faster as time goes on. We passed the point at which computer processors got faster by being faster years ago. Computer processors now get faster by being more and more complicated. Harder to program, harder to use, and I think what that means is that software environments like Galaxy are going to become more and more important in letting us as a community get good use out of these incredibly complicated processors. And after the end of Moore's Law, after it becomes impossible to make processors any bigger, probably then comes quantum computing, and I have absolutely no intuition for what happens then other than the likely prediction that it will be somebody else's problem to solve, not mine. So we got to leave something for the young people to do. Just a couple things about how to use Jetstream. This is the commercial part. So jetstream-cloud.org is the homepage for Jetstream if you want help email jethelp@iu.edu. If you are a U.S.-based researcher, you can, for the price of a couple minutes, get yourself a startup allocation of 50,000 core hours, vCPU hours, just for a few minutes of asking it. You can be up and running with your own account on Jetstream. The staff of the National Genome Analysis Support Center, Tom Doak, Carrie Ganote, who are both around here, will be able to help you, as well as Jetstream staff. There is a request time period coming up for large allocations. So if you've got a lot of bioinformatics going on and you want a lot of time on Jetstream, you can ask for up to millions of vCPU hours in one allocation anytime between now and July 15th. Let's see, what else? Jetstream is funded by the National Science Foundation with the advanced foreknowledge that many of the researchers that use it will be funded by the NIH. It's perfectly fine if you're funded by the NIH. If you are not a US-based researcher, you can still get to use Jetstream if you have a collaboration with a US-based researcher who can actually request the time. And of course, if you're not a US-based researcher, you can still use Jetstream through the Galaxy.org website. So I want to thank the Galaxy community for being here for this conference here at IU, first of all. I want to thank the organizing committee for the great job they've done. The research has been supported by the NSF through 3 grant awards, actually 2 to the National Center for Genome Analysis Support and Jetstream, and any opinions that I have said may or may not be agreed to by anyone at any organization that's given us some money. I do want to thank our partners, Texas Advanced Computing Center, Johns Hopkins University. Enos Afghan has been instrumental in getting this running. University of Chicago, the Globus team, really critical partners in this. UT San Antonio, the National Snow and Ice Data Center. Dell is our vendor partner. We are almost ready to go into production. The NSF has given approval for this system to go into full production, which means it'll be around for a while. We don't have a date set yet, but we are very thankful to Dell because Dell gave us a supercomputer with the advanced knowledge that we were going to spend 1.5 years convincing the NSF to give us the authority to give Dell the money for it. And if that didn't work out, what was going to happen was that Dell was going to get a used supercomputer back. So they've been very, very helpful. Last and not least, use Jetstream. We have metrics that we have to hit. You have science that you need to get done. The more science you do on Jetstream, the better our usage numbers look, and the easier my next annual review will be with the National Science Foundation. But what matters to you is doing your science. And what matters to me about Jetstream is knowing that Jetstream is known not for how big it is or how great the lights on it are. I want Jetstream to be known for the quality of the research that it has supported. Thank you all very much.
I actually have 2, but I'll ask just one. Where do you think things are going? Where do you think we are going to be in 15, 20 years? Are we all going to be performing our analysis somewhere in a cloud center, or how is this going to develop?
Well, I'll begin by saying that that my ability to predict is highly limited, as evidenced by Chile beating Argentina and Iceland beating England in the last couple days. But the question was, what's my prediction about where things are going in the next 15, 20 years? I think in the next 5 years, where we're going is every different direction at once. ARM processors are becoming more and more important in large-scale systems because they're power efficient. IBM has staked its future on the Open Power Consortium. Intel continues to plug along. China has surprised everyone by putting a machine at the top of the list of 500 fastest supercomputers in the world with domestically Chinese manufactured processors. So from a hardware standpoint, it just gets worse and worse and worse for the next 5 years. So I think that what that means is that user interfaces like Galaxy, iPlant, Cyverse, Cypress, they just become more and more important. I think in the long term, say 10 to 20 years from now, what's going to happen is that the amount of power it takes to run a big computing system and the amount of money it costs to move data around will lead us to a situation where we will probably still have significant university-owned IT organizations running their own computing systems, but I think they're going to be off someplace in a data center, maybe someplace where you can get wind power or solar power, and you're going to have large data storage systems, you're going to have cloud systems, data analytics systems, and supercomputers all in one big building where you can cool them effectively and where you can move data around for the price of what it costs to lay optical fibers across the floor. Thank you all very much.